You are in the cockpit of a 60-ton commercial aircraft, descending at 2,000 feet per minute into a completely opaque cloud layer. Outside the window, visibility is functionally zero. To reach the runway safely, pilots rely on the Instrument Landing System, or ILS. This is a network of ground-based radio antennas that construct a highly precise three-dimensional corridor down to the pavement. Pilots navigate this corridor using a two-dimensional document. This is an approach plate, and this specific chart details the ILS procedure for runway 27 left in South Bend, Indiana. While it prints flat on paper, the chart acts as an instruction manual for navigating a complex three-dimensional intersection of radio frequencies in the physical world. The entire system operates on a single comparative mechanism. It measures the relative signal strength of intersecting frequency-modulated radio lobes to pinpoint exactly where the aircraft is in space. The system splits this task into two distinct elements. One array provides horizontal guidance to align the aircraft with the runway centerline, while a second array provides vertical guidance to control the descent rate. Centering a needle on an instrument panel is only the final output of the system. To execute an ILS safely, a pilot must visualize the invisible physics of these radio waves to avoid dangerous, naturally occurring signal anomalies along the descent. The horizontal component of the ILS is called the localizer. Its antenna array sits exactly on the extended centerline of the runway, typically positioned 1,000 feet past the departure end. From that position, the antenna transmits two overlapping radio lobes. The left lobe is modulated at 90 Hz. Simultaneously, a right lobe, modulated at 150 Hz, overlaps it. The course centerline exists precisely where the signal strength of both the 90 and 150 Hz lobes is perfectly equal. Inside the cockpit, a course deviation indicator, or CDI, visually represents this balance. The aircraft's navigation receiver continuously analyzes the incoming radio waves. If the aircraft drifts right, it enters the stronger 150 Hz field, driving the CDI needle sharply left. The CDI operates as a command instrument. It points toward the stronger signal, explicitly instructing the pilot which way to turn to regain the centerline. These specific azimuth signals operate on the very high frequency, or VHF, band, specifically between 108.10 and 111.95 MHz. Horizontal navigation on an ILS is a continuous mathematical comparison of signal dominance. It relies entirely on measuring relative field strength, rather than a linear distance. The localizer beam expands outward from the antenna in an angular cone, usually measuring a total of 5 degrees wide. This specific angle is calibrated so the usable signal spans exactly 700 feet, crossing the threshold. Because the beam is an angle, its physical width changes with distance. 10 miles away, that same 5-degree cone is thousands of feet wide. As the aircraft flies down this funnel, the corridor continuously narrows. A 5-degree heading correction might be necessary initially, but near the runway, inputs must become highly precise adjustments of just 1 or 2 degrees. This spatial geometry creates a specific hazard when an aircraft attempts to use the localizer to land from the opposite direction, a back-course approach. Approaching from the reciprocal heading means moving through the back of the signal. From the pilot's perspective, the 90 Hz left lobe and the 150 Hz right lobe are swapped. This creates reverse sensing. The standard CDI now acts as a non-command indicator. If the aircraft drifts right, the needle swings right, pointing away from the centerline. The navigation receiver obeys raw signal strength without awareness of geographical intent. A pilot must mentally map their spatial relationship to ground antennas to interpret correctly. For vertical guidance, the ILS uses the glide slope antenna. Unlike the localizer, this array is positioned off to the side, 1,000 feet inland. The glide slope transmits on the ultra-high frequency band. It uses the exact same comparative principle, projecting a 90 Hz lobe overlapping a 150 Hz lobe vertically. The zone where these equal forms an exact 3-degree optimal descent path. This vertical beam is extremely thin. The entire usable signal is roughly 1.4 degrees thick, extending only 0.7 degrees above and below. To track the slope accurately, pilots apply a standard descent calculation. Multiplying the aircraft's ground speed by 5 provides the required feet per minute rate. Following this path yields consistent checkpoints. 3,000 feet at 10 miles, 1,500 feet at 5 miles. Drifting outside that boundary means losing the signal entirely. This ultra-narrow vertical beam creates an unforgiving spatial corridor, demanding continuous pitch adjustments from the pilot. Operating UHF radio transmissions close to the Earth's surface introduces a critical vulnerability: signal reflection. A significant portion of radio energy strikes the ground. These reflected signals recombine in the sky, creating secondary, unintended zones where the frequencies overlap perfectly, high above the intended path. This creates a primary reflection anomaly pitched upward at a 12.5-degree angle, known as a false glide slope. If an aircraft intersects this secondary overlap, the navigation receiver detects equal signal strength. Inside the cockpit, the glide slope indicator centers perfectly, providing an illusion of safety. Flying a 12.5-degree slope requires a violently steep descent. The aircraft would dive toward the runway at a completely unsafe speed. Because radio waves reflect upwards off the Earth, this geometry establishes a fundamental rule: false glide slopes exist above the correct path, never below it. Trusting the cockpit instrument blindly without verifying altitude can trick a pilot into a catastrophic dive. Safety relies entirely on understanding this geometric flaw. This chart is the South Bend ILS runway 27 left approach plate. It serves to bridge this theoretical radio physics into practical cockpit application. The bottom section of the chart is the profile view. This is a side-on schematic of the descent path. Notice the initial approach fix at the Misha intersection. The chart indicates a heavy, solid line, instructing the pilot to hold a strict altitude of 2,000 feet. This 2,000-foot requirement is specifically calibrated relative to where the true glide slope begins to radiate outward from the runway. The solid black arrow shows the aircraft tracking inbound along the localizer beam, maintaining that flat altitude prior to any vertical descent. The Maltese cross icon pinpoints the exact physical location where that trajectory intercepts the descending 3-degree glide slope. By maintaining 2,000 feet, the aircraft is flying underneath the primary radio beam. This forces the receiver to intercept the true glide slope from below. Because false glide slopes only propagate upwards, executing this specific geometric profile ensures the aircraft completely bypasses the higher 12.5-degree anomaly. The seemingly arbitrary altitudes published on an approach plate are deliberate navigational boundaries. They are drawn to keep the aircraft within safe physical geometry. The needles on a cockpit display are only surface-level indicators. Precision instrument flying requires manipulating an aircraft through an invisible, meticulously constructed mathematical architecture.